Good afternoon, Year 4, and welcome to your final geography lesson before half term. I'm really proud of how hard you've all worked. It also happens to be our last lesson on earthquakes before we move on to looking at volcanoes after half term. So let's jump into the lesson. So this week we are looking at how can people prepare for earthquakes. So the first thing we need to do is our knowledge quiz. So I'd like you to number 1 to 5 in your notebook and pause me once you do that and unpause when you are ready. Okay, let's get going. So, question 1. What was the magnitude of the earthquake which occurred in Christchurch on the 22nd of February 2011? 3.5, 5.3, 6.3, or 9? Pause me now. Welcome back. It was indeed a 6.3 magnitude earthquake. Question 2. The February 2011 earthquake in New Zealand lasted 1 second, 10 seconds, 1 minute, or 10 minutes. Pause me now. Yes, well done if you said it was 10 seconds. Obviously, that is quite a short amount of time, but a lot of destruction can happen within that time. Question 3. Avalanches are a human effect of an earthquake. True or false? Yes, well done if you said false. Avalanches are a physical effect. Physical effects affect the natural environment, whereas human effects impact the man-made features. So avalanches fall into the physical category. Question 4. Why were the Druids so important in Celtic society? So you need to circle 2 reasons. Pause me now. Welcome back. So well done if you said it's because they were priests and because they controlled much of Celtic law and dealt out punishments. So the Celts did not pray to the Druids, they prayed to their gods. It was the Druids who led these prayers. Question 5. What is a barrier constructed to hold water back called? Is it a dam, a canal, an irrigation, or a reservoir? Pause me now. And welcome back. Well done if you said a dam. Okay, so let's quickly recap. How do earthquakes happen? Tectonic plates are moving past each other at a plate boundary. One of the plates gets stuck. Pause me now and say aloud what the next sequence in the diagram is. Well done if you said it's because the plate is stuck, pressure builds up whilst it tries to free itself. When the plate becomes unstuck, the pressure is released in a wave of energy called a tremor. And it is, of course, the tremor which causes the earthquake. So can we tell when an earthquake is about to happen? Well, the short answer is no. Scientists cannot predict earthquakes. However, we know that they are more likely to occur at tectonic plate boundaries. So if you live in a country such as New Zealand, which we looked at last week, or Japan, these places are more known to have earthquakes because of the tectonic plate boundaries, so people in these societies are much better prepared. But no, we cannot predict earthquakes. People, however, have been trying to think of devices that can predict earthquakes for absolutely years. So this device is from around 2,000 years ago, so just after when they finished building Hadrian's Wall. It was made in China. And it works by levers are being attached to a pendulum, which is inside the bronze jar. When an earthquake shook the jar, the pendulum moved, which would cause one of the balls to drop out into the mouth of a frog. So people would try and use this device as soon as the ground started shaking to try and prepare themselves within a few seconds for an earthquake coming. Obviously, nowadays, we do have slightly better technology to help us with the detection of earthquakes, but more likely that these type of machines are used for recording earthquakes. So my turn, your turn, seismograph. Seismograph. So a seismograph is an instrument that records the waves caused by an earthquake. Seismographs are now sometimes called seismometers, which are a more digital version and can be connected to more technology. So seismographs They might be able to detect the smaller waves at the beginning of an earthquake, which might give people a few seconds to prepare, but usually they're used just to record earthquakes as they happen so that scientists can study them afterwards. So we're just going to watch a video on how a seismograph works.
How a seismograph works. A seismograph is an instrument used to measure the movement of earthquakes. A weight is suspended in a way that allows it to remain still when the ground moves. Most modern instruments use an electromagnetic mechanism for this. A writing instrument is attached to the weight, allowing it to record the movement as it happens. The word graph refers to the writing action. Most modern earthquake monitoring uses seismometers, not seismographs, and record the movement of the Earth digitally, or output the data to a seismogram, a printed version of the wavelengths on a large drum. These wavelengths that represent Earth's movements are so small that in order for scientists to study them, they have to be amplified.
So by amplified, it means that they have to be made bigger in order for scientists to be able to see them because they can be so small. So if we can't predict earthquakes, why do we measure them? So seismographs can pick up small tremors, which can indicate that a bigger earthquake is coming. So as we can see on this diagram, it's quite steady, and then the tremors start to get slightly bigger. So you might only have a few seconds or a few minutes before the bigger earthquake comes, but obviously these seconds and minutes can be life-saving time. So if a seismograph picks it up, many countries now can send you a text alert on your phone, which might warn you that an earthquake is coming and you're going to prepare for it. So the tremors that it picks up are kind of like aftershocks, the little bit of shaking, but it's before the earthquake. So earthquakes are measured on the Richter scale. My turn, your turn. Richter scale. Richter scale. The Richter scale is used to measure the intensity of earthquakes, so how strong an earthquake is. So for example, the Christchurch earthquake was 6.3. So if we have a look on this model here, if we go to about 6.3, it's the potential for destructive tremors. So obviously the further down this way it is, the less severe or intense the earthquake is. Getting up to 10, that is extreme destruction. Now there's never actually been an earthquake measuring at 10. So you can imagine how destructive 10 actually is. Most earthquakes that are really destructive in this day and age are about an 8, somewhere between a 7 and an 8. So here we have a bit of a further breakdown. So if an earthquake is measuring at less than 2, you can call it a microquake. It's not even really felt. So there's approximately 8,000 of these per day. That's a lot, but obviously it's called an earthquake, but it's not as an earthquake as you or I might imagine it or that we've learned about. Coming up to 4, it's a light earthquake, so it can often be felt indoors. So, you know, some indoor items might start shaking, there might be rattling noises, but no significant damage is caused. So there are around 6,200 of these per year. So that's more than one per day because we've got 365 days in a year. So, you know, they're quite frequent and they don't really cause much damage. We then maybe come to a 7, which we'd consider a major earthquake, and it's known to cause severe damage over large areas. So this would be the sort of earthquake that Christchurch was a 6.3, so we saw the destruction in that, so you can imagine that 7, it's just becoming that increasingly bit destructive, and there's about 18 of these per year. And then, as I said, the 10 on here, it can't be estimated how many there are because there's never actually been one recorded. So what I'd like you to do now is number 1 to 3 in your notebook, and pause me when you've done that. Sorry, pause me and then come back to me once you've done that. Okay, welcome back. So I'm now going to show you some earthquakes, and you need to choose a range on the Richter scale which you would place these earthquakes into. So by range, I just mean, for example, 5 to 5.9, that would be the range. So I'm not expecting you to guess exactly what it is between there. You're just going to choose a range. Obviously, we have different descriptions for each range. So we'll go An example together first. So this isn't number one, this is just an example. So I've been told that there's serious damage over a large area. This is an earthquake that happened in Haiti in 2010. So let's watch the video. I've told you the answer already for this one. So the range is 7 to 7.9. The actual earthquake was a 7, but you would just have written down 7 to 7.9. So as we can see in this video, there is serious damage over a large area. This drone flight is showing us that it's not just one or two houses or some streets, it's a big area that was damaged. So you'd rate that one at 7 to 7.9. Okay, so here is your first one. There's no video this time, it is just pictures. So the description is that there's no significant damage. There might be rattling of items. As we can see in this picture here, books have fallen off the shelves in a library, and in this woman's house, her pictures have fallen down. So if you need to pause me and rewind the video to look back at the chart that I showed you, you can do that. Or if not, make a good guess at what you think that this earthquake, the range it would fall into. Okay, welcome back. So this earthquake was a 4.9. So if you wrote down the range of 4 to 4.9, you were correct. So between a 4 and 4.9, there's no significant damage, it's just a rattling of items. So this was in Ridgecrest in California in 2019. Okay, on to our next one. So we've got the information that there was serious damage over a large area. This earthquake happened in Nepal in 2015. So let's take a look. Okay, so again, in this one, we can see that there's quite a lot of destruction. There's many buildings which have fallen down. People are out on the street. So pause me now and write down your prediction for this earthquake. So yes, well done. If you said it is a 7 to 7.9 again. So we've been told of serious damage over a large area, which we could see. So this earthquake was actually a 7.8, and it's been one of the most destructive ones in recent years. Okay, moving on to our last one. So this time we have down that major damage can be caused to some buildings, little or no damage caused to well-constructed buildings. So take a look at the picture. Obviously we have one building here which has collapsed, but we can see around that there are other buildings which are still stood. So this earthquake happened just a little bit over a year ago in Turkey. So pause me now and write down your prediction for what this earthquake measured on the Richter scale. Okay, welcome back. And well done if you said it was in the 5 to 5.9 range this time. So it was a 5.3 magnitude earthquake. So here's a little recap. So the first one was a 4 to 4.9, the second one 7 to a 7.9, and the third one a 5 to a 5.9. So using this chart, it helped me find the answers. So how can we prepare for earthquakes? Now we're very lucky in this country because we really do not get many earthquakes at all. So it's not something we have to really think about. There's rarely ever been any destructive earthquakes in this country. But how can we prepare if we lived in a country that did have lots of earthquakes, such as New Zealand or Japan? So there's lots of things that we could do around our house or in school. So you might need to fasten bookshelves and cabinets to the walls so that they're not loose standing. Hang pictures and mirrors away from beds and where people sit, because obviously you don't want them to fall off the wall and hit you. You need to identify safe places outdoors, so away from buildings, electrical lines and bridges, where you might be able to go for safety. You're going to need to teach your family members how to turn off gas, electricity and water, because obviously if you can turn off things like gas and electricity, it decreases the risk of a potential fire. And you're going to need to identify safe places indoors for shelter, so you're under sturdy furniture, against walls or away from glass. So there's lots of things that people can do to make their environment safer if there was going to be an earthquake. So let's have a look at what the advice is for humans to do. So drop, cover and hold on. We're going to watch a video of an earthquake drill in a school in America, and this is what children in countries or areas that are more prone to earthquakes are taught from being very, very young to do quickly.
Good morning, clear signal has come. At this time, we are now in the earthquake drill. All right, boys and girls, colleagues, this is the all clear for our earth.
Okay, so as we could see in this video, the children dropped to the floor. They took cover under their tables and then they held onto their tables to make sure that obviously if it was shifting, they'd have a firm grip on it. So that is the drop, take cover and hold on sequence. So hopefully when we're back in school, we might be able to practice that ourselves in our classroom. So besides the things that we could do in our everyday lives, there are things that some countries are also able to do on a bigger scale. So in richer countries, engineers have begun working to design and build earthquake-proof buildings. So we have an example here of an earthquake-proof building in Dubai. And this is done through something called base isolation. So base isolation allows buildings to not be connected directly to the ground. So they remove the foundations from being connected directly to the ground. And what they do is make sure that during the earthquake, the foundations and the base of the building shake in the opposite direction to the earthquake waves, which counteracts the force. So this can actually make buildings really quite earthquake proof. So for example, in California, the Transamerica Pyramid is one of these buildings. And in 1989, so around 30 years ago, a 6.9 magnitude earthquake struck the area, which caused the top story of the structure to sway by almost 30 centimeters, so about the length of one of our rulers at school. The top was swaying that much from side to side, but the building stood tall and undamaged. It didn't fall down, even though it was swaying a lot. So this has proven to be quite successful. Here we have an example of an earthquake-proof bookshelf. So in this case, they've built the bookshelf directly into the wall, which would stop the unit coming and hitting you. And perhaps we can't see it, but perhaps they also have ways of keeping the books on the shelf if an earthquake was to happen. You can see a Harry Potter book here, always makes me happy. And here we have some scientists who have just developed an earthquake-proof table. So when we watch the video, the first table they're going to show you is a non-earthquake-proof table and what can happen if a big piece of debris or rock hits it. And then it's going to show you the earthquake-proof table that they have developed.
Two Israeli inventors have come up with a design for an earthquake-proof table they hope could save thousands of lives in quake-prone developing countries. During earthquake drills, children are usually informed to hide under their desks, potentially deadly advice if the desk is not strong enough. The earthquake-proof table consists of a steel frame with a birchwood tabletop and is designed to spread the weight of a significant down force evenly across the table, while dispersing the debris to the sides. In tests, it has successfully withstood weights of up to 1 ton. Its inventors say the table has the potential to help up to 300 million children who live in earthquake zones where building standards are lax. The table is now awaiting approval from the world-renowned structural engineering department of Padua University in Italy.
So there was another example of how some great engineering is helping us to build things which can protect us from earthquakes. So in countries like Japan and New Zealand, like I've said, where they get more earthquakes, these sorts of things can save lives. Obviously, we wouldn't need them in this country because we don't get earthquakes, well, at all, really. We get them very, very rarely, and they're not very severe. There's also been developed an earthquake-proof bed, which I'm not sure about myself. I might feel like I'm a bit hidden there. But an earthquake-proof bed has been developed in Turkey. It automatically senses large tremors under the ground and closes around you. It's equipped with air vents so you can still breathe. So obviously this would be if an earthquake was to happen during the night and you didn't have a chance to quickly get under a table or a desk in your house. And they've developed this bed which should help protect you. I mean, you might think that this looks a bit not very nice, like a bit like a coffin. But, you know, some people, if you live in an earthquake-proof country, an earthquake-prone country, sorry, this bed might give you a bit of peace of mind that you'd be safe sleeping at night, just in case. So for your activity today, I would like you to complete a risk assessment of your house. Now, obviously, as I've said, an earthquake isn't going to happen here. It's not going to happen to your house. We're just imagining if we lived in a country, if your house was planted in a country where earthquakes are more likely to happen. So you can do your house or you can do the classroom. And I would like you to identify 3 potential hazards in your home or classroom if an earthquake were to strike. So you need to obviously, first of all, identify the risk, say why it is a risk and how you are going to reduce this risk. So let's take a look, first of all, at my example. So I did it for our classroom. So this is Newcastle class when it was nice and tidy at the beginning of the year. So I looked at this picture and I tried to identify things that I thought might be a potential hazard if an earthquake was to happen. So the risk I identified first was that there are exercise book boxes on the desk and they're not currently secured to the desk, they're just balancing on their loose. So why is it a risk? So when the ground shakes, this will cause the desk to shake and the boxes and books might fall off and injure someone, they might hit somebody. So how am I going to reduce this risk? I'm going to ask Miss Jones to buy some strong Velcro strips to secure the boxes to the tables to stop them falling off. So for example, one that you might have at home, it might be that you know in your room you have a bookshelf which isn't attached to the wall. We've discussed why that's a risk. Obviously it might fall and hit somebody, and how you're going to reduce it, you're going to attach it to the wall. But there's lots of different things we've discussed and things that we've looked at. So have a look around your house or come to these pictures of the classroom and have a go at doing a risk assessment. If you can't print off the sheet, as I've said, don't worry. I just drew my own table here, or you can ask an adult to help you draw a table that looks like this. So if you need this slide, pause the video on this slide, pause on this slide, or pause on this slide and complete the activity. Okay, welcome back. I'm very excited to see your risk assessments on Seesaw later, and your other teachers are also. So I hope you have enjoyed our lessons on earthquakes, and I look forward to seeing you next week, or after half term, should I say, for our lessons on volcanoes. Have a great rest of your day, everybody, and well done for all your great geography home learning.